I've got very much synthesis on the brain. Currently, we're conducting a search for a synthetic chemist in our department, and so the title sort of came out of just having it on my mind. Anyway, the cartoon is actually supposed to indicate the idea of bringing these two things together, rare event sampling to search out conformational landscapes, and machine learning to help us understand what's going on with these landscapes. All right, so before I start, let me just acknowledge the people I worked with on this particular project. So a lot of this work was actually done in collaboration with my colleagues at NYU Abu Dhabi, one of our 3 global campuses, right? And so this was done largely in collaboration with my colleague Said Al-Kirmizi-Altan, who was one of the theoretical chemists there, our joint postdoc Nawavi Nalim, and Charles Abreu, who has been working with us to develop a lot of things I'm going to be telling you about and putting it into the OpenMM code. And then as well, our collaborators Nishant Nair at the IIT in Kanpur, and 2 students, Buchen Tong and Shitanshu Bajpai. Okay, so Cecilia mentioned the idea that having a point or a handful of points on an energy landscape, however important they are, is only part of the story, right? And you really want to have a picture of the full landscape as much as you can actually generate it. But we know why that's challenging, right? We have this thing called the rare event problem, which makes it difficult to explore all the possible minima you have on an energy landscape. You may have lots and lots of minima separated by high enough barriers that you don't get to cross them very often in an ordinary molecular dynamics exploration of your landscape, all right? So I'll show you an example, and I like to show this one a lot at the IPAM because it illustrates really what conformational sampling looks like. So this is an alanine decamer. And if you think about just one of the residue pairs in there, and you extract it, you ask, well, all right, along this backbone, what might I want to sample if I focused in? And the sort of the important angles that we think about, the variables that really characterize the free energy landscape might be these 2 angles here, phi, psi, maybe theta plays an important role. But the movie that I'm going to show you targets on this alanine decamer all of the phi psi pairs, and this is in vacuum. And the landscape is actually kind of interesting when you do this. Right? So this is, in a sense, a 20-dimensional landscape that we're generating. It's a decamer. There are a pair of phi psi angles for each residue. So that gives you a 20-dimensional landscape. And we like looking at things at this fine grain level. Now, when you target these for enhanced sampling, you find a kind of rich landscape going on. I can see this thing folding into a helix. It will unfold and form a hairpin from time to time. You'll see a bunch of other kind of metastable conformations. And as you watch this movie, you can literally see the distribution forming before your eyes, right? I mean, you can see very clearly that the hairpin forms, that it's not as stable as the helix, and any other conformations that you visit are certainly metastable in terms of the free energy ranking that you're getting here, right? So you can really see from enhanced sampling what that distribution looks like. And on this, high-dimensional landscape, you can analyze the conformations of interest. You can try to drive the simulation from one basin to another. And for example, if I wanted to know on this landscape, well, what's the free energy change in going from the hairpin to the helix? By analyzing this landscape, I find that it's, for example, 40 kilojoules per mole downhill. So the helix is more stable by 40 kilojoules per mole. And you can kind of see from the movie that that's really what's happening. And that compares well with, this sort of old calculation of Benoit Roux using deactivated morphing. They got about 42 kilojoules per mole downhill to get to from the hairpin to the helix. Okay. So looking at things at this fine grain level is really interesting. How do we actually do this kind of sampling. So I want to take you through the sampling approach to generate these high-dimensional landscapes that we use. And then I'll try to bring in the machine learning aspect to tell you sort of what we're getting from these high-dimensional landscapes. So I've talked about this a lot at IPAM, so just to go through it again. Let's suppose you've identified some set of collective variables that you're interested in. Now, these may come from your brain, they may come from some kind of machine learning protocol. Whatever it is, you've got some variables that you think characterize your landscape, and you want to try to generate a free energy as a function of these things. So what does that mean in terms of statistical mechanics? That means that you have to solve this problem, right? So I have a potential energy, I need to integrate over all the conformational space. I set a condition that my chosen collective variables have certain values, and when you do that, restricted integral, you get what's called the marginal probability distribution, and it's that defines for us the free energy. You take the log of it, multiply by kBT, and that gives you your n-dimensional free energy landscape. Okay. All right, now, doing this on an n-dimensional landscape, imposing all these conditions is extremely expensive. If n were 1, I could actually maybe do a constraint and map this out as a function of n on my one coordinate on some one-dimensional grid. If I had 2 degrees of freedom of interest, I could really, if a brute force calculation, I could do it on a 2-dimensional grid. But as you introduce more and more collective variables, the size of the grid you'd have to generate gets really huge. You have a kind of exponential explosion of the number of points that you would need, all right? So if I want to do a 20-dimensional landscape, I'm not doing it by imposing these conditions. Rather, what I want to do is to try to sample this marginal distribution on the fly. Right? So how will I do that? I don't know it a priori. But just like we generate, sample a Boltzmann distribution in a Monte Carlo molecular dynamics calculation, I claim, you can actually sample this marginal. How would you do it? So the first thing you need to do is to clear these delta functions. So you turn them into Gaussians that are very narrow and highly peaked, right? And when you do that, when you write it like this can then be absorbed into your Hamiltonian as a kind of additional potential. So if I want to sample the marginal, I can treat these S's as dynamical variables. In other words, I'll extend my phase space, and I'll do molecular dynamics on a Hamiltonian that looks like this. So that's my original physical Hamiltonian. I add in this potential energy that looks like a harmonic coupling between the S's that I have to sample and the degrees of freedom of my collective variables of interest with some spring constant. And then to move things around, I have a kinetic energy for them with some fake masses, all right? And that is the thing that lets you sample, okay?
I can see why you might want to do this, but I mean, the simplest isn't the simplest thing that if you sample just from R and then you just evaluate your S's and just from, I mean, if you can sample the high dimensional joint,
yes,
then you can just evaluate your Q of R, and then you just,
that's the rare event problem.
Yeah, that gets the original problem again, right? Yeah.
No, sure, but I just meant, okay.
I'm trying to overcome that, right? So
Sure.
let me take the next step, and maybe it'll answer your question. So in principle, this will sample something, right? But it won't actually sample the marginal of interest. What you have to do is to play around with these fictitious masses, and the key thing that you need to do is to make them heavy. So in other words, I'm going to a kind of a Carr-Parinello-like limit in which I make these things heavy compared to all the other timescales, the physical timescales in the system. And that will ensure that I can sample the marginal, because these S's will move slowly on the timescale that my R's move around, right? And so it'll locally sample the configuration space. Yes.
It is a very quick clarification question. So is this an actual, do you mean it's a probability distribution?
Yes.
Or is it actually more like a partition sum? Because I don't see the normalization constant there.
It doesn't matter. The normalization is just a constant in your free energy, so it's irrelevant. Yes, it is a unnormalized probability distribution.
Okay. So okay. So it is actually also like a sum. Okay.
Yeah, think of it as a restricted partition function. But it is a marginal because I have to map it out in terms of all these S's. Right?
Yes, sure.
Okay.
Mark, what about the harmonic constants? Do you just choose them? Are they all the same, or you choose them?
They can be different for different, depending on what your collective variables are. They don't have to be the same.
So if you have just 5 psi, you would set them to the same value.
And then I would use the same value, yeah. If they're all the same type, you can make the k's the same, the kappa's the same. Okay, so I make this decoupling, this adiabatic decoupling condition, and that ensures that I'll sample the marginal, but I'll sample it very inefficiently. So in order to make this thing efficient, I introduce a high temperature to go along with it. So I make sure that these S's are being sampled at high temperature, all right? So I have this adiabatic decoupling, I have this temperature boosting, and so you would basically implement these equations of motion with some heat bath, whichever one you like. And what you can prove about these equations that is you sample these S's, and let's say you're kind of sweeping over the landscape. You're generating a scattering of points over your potential energy surface. So what I can prove is that if I calculate a histogram or some sort of distribution of these S's at this temperature Ts, well, that's going to be also related to a free energy. As I'm sort of waving my hands here, there is a more rigorous proof of this, right? But I think of this as being related to the free energy but generated at this high temperature, then I can simply say, well, this has got to be given by my original marginal raised to some power. And so that's the original marginal raised to a power of T over Ts. Now, T over Ts is fractional because this Ts is high. So if I think about the original distribution, what this is doing is it's kind of softening the distribution. It brings the low probability regions higher, the high probability regions lower. It makes things more democratic. You can sample more efficiently. But this simple relationship means that if you take the log of both sides, you bring this T over Ts factor down. So if I multiply by KTS, the TS's will cancel. I get KT log P, and that is the free energy back again. So this is my very unrigorous proof that the method works. If you look in our papers, we have a much more complicated dynamical proof using Liouville operators and so on and so forth, which I don't want to get into, all right? But this gives you an idea of why this works. Okay. Now, I know everyone sort of likes metadynamics, and it turns out that you can combine this nicely with metadynamics. You can make everything interoperable. So this is the original approach. We're sweeping over the landscape at this high temperature. But let's imagine now that I want to add a bias on my landscape in order to help further boost the sampling. So I can add a metadynamics bias, but I'll do it in this S space, not in the physical space. It's a little bit different from the metadynamics that everyone knows and loves, all right? But you can put this in there. And so as you're sweeping over the landscape, you're dropping these Gaussians. And that helps to further, boost your ability to cross the barrier. Now, let's suppose there's, in addition, one coordinate, I'll call it S1, that's really hard to sample, like maybe an RMSD or something like that, all right? You can add that in as an umbrella coordinate, right? And you can do umbrella sampling also in this S space. So all of these things are interoperable. I can combine temperature boosting. I can put metadynamics on any set of these variables that I want. And if there's one in particular that I want to focus on, I can add yet one more bias, an umbrella potential there too. Okay, so all of this is now available if you want to play with it in our implementation in the OpenMM package, which is a molecular simulation package. And very easy to build your own kind of customized simulations. And we have a publication coming out on this that shows you how all these things work together synergistically. Okay, so let me just give you an example of this. This is how I did that alanine decamer, but let's do something a little bit more complicated. So this is the trip cage. This is this 20 residue mini protein that folds on a relatively fast time scale. And we're doing a set of basically 9 collective variables here, if I've numbered these, right? So these 6 plus these 3, these 2 in addition. So 8 collective variables, right? And you can see how I've partitioned things. So the RMSD of the alpha carbons, they get the metadynamics bias. The radius of gyration of the alpha carbons, they get the metadynamics bias. And then all of these are just getting temperature boosting, all right? They're getting the adiabatic free energy coupling, okay? And so this little movie, what you're looking down here is the RMSD, so the first collective variable, and you can see how this thing moves away from its folded state and then finds it again, all right? So it goes to some kind of random coil-like thing and then comes back. And if you run this movie longer, this just keeps unfolding and refolding, unfolding and refolding. Okay. Oops. Now, if I want to analyze this a little bit more, let's suppose I now change the RMSDB to be an umbrella coordinate. As I said, that can be something that could be useful. And you get this really nice projected free energy landscape. Right? So I have an 8-dimensional thing, but I'm projecting it for you down into 2 dimensions, RMSD and RG. And you can clearly see, this is the unfolded state. There's a kind of wide basin here with an intermediate. And then here this thing narrows into a funnel-like folded state, right? Now, to some extent, the number of features that you pick up is going to be determined by the number of features that you use to represent your free energy landscape. So I show you 2, and I pick up maybe a couple of key conformations. What if I added 3? All right, so what if I actually did, in this case, RMSD, the Saltbridge collective variable, and also here on the third axis is this helical RMSD. So it's a different projection altogether, right? And here you can see that you pick up more features, all right? So my unfolded state is there, but I have a number of other kind of metastable intermediates. And if I added more axes to this, I'd pick up yet more conformations, right? Okay. In this case, because we're able to generate this landscape, I can compare the folding, the change in the free energy between the unfolded and the folded state, which is about 0.8 kcals per mole, and that agrees nicely with this experiment of George Makatanzi's group. Right? You can also look at the convergence with time of some of the free energy differences between folded and unfolded or intermediate and folded. And pretty much this thing is converging on a time scale of tens of nanoseconds. All right. Now, I said that there's a lot of features. One of the things that you gain by sweeping over the landscape with this temperature boosting is the ability to see features in a way emerge, all right? So what we've been doing as one of the ways to employ machine learning is to say, okay, well, if I just give you a random, sort of a scattering of points that comes out of my simulation, all right? So this is looking at a phi-psi pair on one of my alanine-based oligopeptides. You can actually just use the points that you've generated so far as inputs to a neural network and let it output for you, the fit, the neural network representation of your free energy. So this is just fancy nonlinear regression, right? But so if you look at this scattering of points, well, I don't see much in terms of the features. But if I let the neural network kind of tell me what's there, I get this 2-dimensional plot. Okay, so you can see real features there. And if you add more points, let's say we go here and I double it to 100 points. Now I get that, because I'm sweeping over the full landscape. So as I move from one basin to the other and I revisit them, I get a more dense scattering of points. And so the neural network now starts to resolve more of the features. As you keep going, your density of points, sample points, generates, you retrain your network, and these features are just emerging. At some point, they just stop changing, right? And of course, you could turn that into a learning curve, and it would look something like this, right? So by the time you get to, several hundred sampled points, you've pretty much got your L2 error down to something pretty low. Okay. Just to point you to this paper where we compared a number of different kinds of methods, so kernel methods, neural networks, weighted neighbor methods in terms of their ability to regress these surfaces. And the bottom line is you can read how the comparison goes. So the bottom line is that the neural networks pretty much outperform all the other techniques. Now, as I said, once you have these surfaces, you can deploy these surfaces to compute some sort of observable that you might be interested in. All right. So the way you do that is you'd say, okay, well, as long as I'm doing a sampling of a conditional or a marginal probability, anything that I want to, whose ensemble average I want as an observable, can simply be collected as a function of these S's, all right? And then, you can weight it with a Boltzmann factor of your surface, and then you get your observable that way. Whoops. Sorry about that. Okay, so here's an example computing the NMR-J couplings for this little 5-residue peptide. This is called metenkephalin, as a function of the number of training points that I use to generate the surface. All right, and again, I'm using the full set of backbone dihedral angles in this surface. So it's a 5-residue peptide. That's 10 dihedral angles. That's a 10-dimensional surface that I'm generating and deploying. And you can see, that you get a mess, but eventually these things do kind of converge to very nice, well-defined values after maybe 30 or 40,000 training samples. Okay? And these points out here are what you get by just brute force sampling the configuration space. That takes several microseconds to actually get these to converge. Whereas these things with your machine-learned free energy surface, you can get it in a few tens of nanoseconds, which is all the time you need to generate this number of points. Now, with a 10-dimensional surface, how featured is this thing? Well, okay, I can't show you a 10-dimensional surface, but I can put all the points that I get on a sort of a sketch map generated graph, and it looks like this, and there's about 1,000 minima there and something like 1,500 saddles. So the minima are blue, the saddles are red. They sort of cluster around these various key conformations. And then on top of that, I can put the free energies that I get, and I get a picture that looks like this. So those are my most important conformations. So when I generate these observables, I'm using the full 10-dimensional surface. I don't know a priori that I need the whole thing to generate these things, but I'm looking at, these NMR-J couplings are functions of the backbone dihedral angles. And so presumably I do need lots of the features to get these things to converge. All right. So when deploying these landscapes to generate observables, you might need a lot of detail. In terms of understanding them and interpreting them, maybe not so much. Okay. So
question. Notationally, I'm a little confused. Like, you're doing this average over the 10-dimensional S space, but this operator that you're trying to get the expectation
that's correct.
Is written
Yeah.
O of R.
That's right.
And then of S. Like, how do you? I mean, O of R means you're averaging over all the R's. Is that?
But it is, and that's how originally this thing is averaged over the R's, right? But I have, I'm generating this against the marginal distribution. In other words, as I generate the marginal, I'm also generating something that's itself a function of the S's.
Right. So in order conditional distribution.
Like a conditional.
How are you? I mean, that seems like a difficult average on its own, right? I mean,
it's about it. Well, it's about the same level of difficulty as generating your marginal distribution to begin with, right? Now, in this case, okay.
I guess I just don't understand how you're. I mean, like, how do you mechanically evaluate that expectation?
So as you run your simulation, right, your physical space is being run at physical temperature. But of course, you have this extra term in there, which is generating a kind of a conditional thing. It's a harmonic coupling. But then I'm also moving the S's around, right? So this thing is then being generated. You just collect this thing as a function of your S's.
But, I mean, you're doing that in like bins of S's? I mean, because S is also continuous and stuff, right? So, and that's moving around.
Yeah, so I would do it as, in terms of bins of S's. Now, okay, but, full disclosure, in this particular case, the thing that I'm averaging to get these NMR-J couplings is actually not a function of, it's just a function of S. It's just a function of, so it's an easy one, right? It's just a function
because otherwise it seems like, 10-dimensional bins of S is like not, that's
so, yeah, well, so, and then what we do when we actually want to get this average is, so I have this machine-learned representation of my surface. I could do the same thing for this if I wanted, right? But here what I'm doing is I'm saying, okay, I'll just sample from this using Monte Carlo, and then I evaluate that. Okay. So there's a lot of detail, right, in there. And that may not be the thing that you're always interested in, right? But if you want to sort of narrow down your high-dimensional conformational landscape, it's sort of hard to think about how to do that. First of all, I'm not going to be able to generate it entirely from scratch, most likely, just given the configuration space. That's very hard to do. So usually I want to have some set of input features, but those features have to describe something. So more often than not, I'll be interested in some specific conformational transformation, and I'll want to know, well, what is the reaction coordinate that takes me from one state to another, like an unfolded state to a folded state, or a hairpin to a helix, or any of the things that I've shown you. So one of the ways that you could maybe do this is to work with machine learning, classify some of the different conformations that you have, and create a classification network, and then work in classification space, create a path from A to B in classification space. Now, I'm not going to talk about that because Yuta, who's in the audience, is actually going to talk about that later in the week. All right, so from the work that we've done there. What I want to talk about instead is learning a committer, right? The thing that basically says, if I start from some point in my landscape between A and B somewhere, and what is the probability that a trajectory launched from that point, wherever it is, will end up in one of the basins, let's say basin B, before it goes to basin A, right? And this distribution, this function of R, this scalar function called the committer, is thought to be a kind of ideal reaction coordinate to describe the transition between these two states, A and B, whatever they may be. Okay. And the idea is that, if you, along this committer distribution, you might find a very nice dividing surface where the probability is equal to go from A to B. And if you think in terms of a transition state, that would be where that is. Okay, so how might we actually learn a committer? Well, one of the ways that you can do it is to say, okay, let's suppose I have a very large set of putative collective variables, probably redundant, all right, but they contain a lot of detailed information in them. And I'll use these to build a picture of my committer. So I'm not starting from the full configuration space. I'm just starting from a large set of collective variables. And some linear combination is assumed to give me the committer with some coefficients. I have to learn these. Okay? So I'm going to call this method 1, and I'll show you how well that works within different machine learning frameworks. The other way you can do it is to say, well, I really want to know what the reaction coordinate is. Okay? So let me actually represent the reaction coordinate itself as a linear combination of CVs, and then I'll model the committer as some sigmoid function. All right, maybe like this. That's a function of my putative reaction coordinate, this thing that I'm trying to model. And the sigmoid behavior is basically right. As you get closer to basin B, the probability should go to 1 that you get to B before you go to A. And as you sort of start closer to A, of course, the probability goes to 0. And there should be a point right in the middle where it's half-half. Okay, so I'll call this method 2, and I'll compare these two things with each other. All right, so in order to train my model, I'm going to have to generate some training values of the committer, which means I have to do some kind of transition path sampling between A and B, right, to generate these committer values. So in this case, we're using something called aimless shooting algorithm, where you sort of sample a lot of points around your transition state randomly, and then you just basically launch the trajectories and see if they go to B or to A first. And once you have that data, there are a couple of ways you can set up a cost function or a loss function for this. One way is to say, well, it's like a classification problem, all right? It is to say I either go to B or to A. So let me write down a kind of cross-entropy cost function, wherein I have my target values here, I have my model here, and optimize that with respect to my parameters with, using some regularization function. All right, and you can do that also with method 2. Here, instead, you would put in your model for the committer. Or the other way you can do it is to say, well, it's maybe like a standard regression problem. Right? So I've generated committer values, so I'll use a least squares type cost function. right? And the regulators that you might use, well, you'll see that we've tried, simple ridges, we've tried lasso, we've tried elastic net. You'll see these acronyms running around. Okay? So standard regression, binary classification, these are two ways you can do it. And in fact, we've done a much more extensive comparison of different machine learning approaches of different types. So we use a whole bunch of standard regressors, including the two that I showed you, Huber loss, ridge loss, Bayesian, orthogonal matching pursuit, various other things, all right? We've looked at decision tree methods, random forest, extra trees, decision trees, boosters, okay? So we've looked at gradient boosting, adaptive boosting, and this one that I'm showing in red, which actually turns out to be our best performer, which is the gradient boosting. Now, in the decision trees, we're always basing our splitting rule on a simple, try to find the lowest variance for, your basins. And then, we actually use these decision trees in our gradient boosting algorithm, all right? So the so-called light or weak learners are decision trees. But in gradient boosting, your weak learners are based on the derivative or the gradient of your loss function with respect to whatever model that you're trying to generate. So you kind of add additional weak learners as you go through this loop, and finally you generate a kind of it looks like a basis type of representation of your model that just gets better and better as you add more and more of these learners in there. Okay. So let's look at a simple example of the alanine dipeptide in vacuum. This is always your starting point. And we're going to look at the conformational transition from these one state to the other. So the C7 equatorial to the C7 axial state, right? And in order to do this, we need to sample some committers. So this is a set of sampled committers that we get. All right, and as you said, depending on where you start, your probability could be 0, 1, or around 1/2. It kind of reaches a little plateau there because a lot of our starting points are around the transition state. Okay, so you get a distribution of committer values, and it has this nice peak around the middle, which is what you'd want to see. And we separate them obviously into a test set and a training set. A training set and a test set so that we can evaluate how well we're doing. All right, here we go. So we're going to use all of the dihedral angles to construct either our reaction coordinate or our committer directly. In fact, we're using the sines and cosines. So this thing has 45 dihedral angles, and so 90 sines and cosines. And so this is sort of the most information that you could put into it. And in order to generate the starting basins, we do enhanced sampling of phi and psi. And so in a sense, you're starting from the beginning. You're saying, well, all right, let's generate a landscape. Let's find two interesting basins, that's here and here. And then I'm going to study the transition between them. Okay, and so this is the comparison of all of the machine learning methods that we use. You're looking here at the root mean square error of your committer. And in method 2, you're looking at the root mean square error of your reaction coordinate and the correlation, the R squared value, right? In terms of, for these linear least squares and lasso, so for these we didn't generate R2 values because the error was so high. But if you look, you can see that, yeah, indeed, the best performers are actually one of these decision trees, the extra trees, and certainly the light gradient boosting is doing it extremely well in both methods. Now, the error here, you have to be a little bit careful about this because it's unnormalized. So the PB is on a range of 0 to 1, whereas the reaction coordinate being composed of sines and cosines is on a -1 to 1 scale. So, you have to kind of divide that by the proper normalization to compare these errors. So they're doing sort of reasonably well, both of them. All right. Let's look at how well we're generating our experimental values, so our actual sampled values. So that's the light gradient boosting. And this is this binary classification, this cross entropy. method. And overall, you can see that the light gradient boosting is getting a much tighter collection of points around the diagonal. So your predicted values are doing much better compared to your experimental values compared to this one. All right. Now, when you have so many features in your model, so many things that you're putting into your reaction coordinate or your committer, you want to see which ones are the most important. Right? They can't all be important. So what we've been doing actually in this is to use something called SHAP analysis. Right? And this can be found in this 2016 paper. So the idea of SHAP analysis is that you take a feature of interest. So let's say that's the ith feature. And you divide all your features into all possible subsets, all right? And so you train your model with the feature you want to focus on, and you train it without that feature for all subsets of your descriptors. And then you sum over all of your subsets with this combinatorial coefficient in there. And then once you do that, you get a score for that particular feature. And this will tell you whether a feature is important or not. So what you're looking at when you sort of generate your score, you get a plot that looks like this called a SHAP plot. All right, so every dot in the plot is one of the observations of your data. High values and low values are basically the high and low values of your features. And then a positive and negative value of your score will basically tell you whether the high or low values of features are pushing you toward one basin or the other. So in terms of, let's say, the committer, that would be pushing you toward 1, or in the high case, or 0 in the negative case, low case. All right, so it'll tell you, how that particular feature is influencing where your system is going to go. So let's look at this. So these are the actual SHAP plots that we get for this alanine dipeptide for methods 1 and 2. And so you can see, that the top features here are these phi angles. Now, phi 2 and phi 3, if you look at my little table, 2 and 3 are basically 5, 7, 9, 11, or 5, 7, 9, 15. It's essentially the same angle, right? So it's a rotation around this particular bond. And then the other features of importance are theta, not psi, but theta. All right, so theta 2 and theta 3 are 2579, 6579. So 6579, 2579, again, it's basically a rotation about that angle. So it's more or less the same feature. So phi and psi apparently are the most important. And both of them are sort of predicting the same thing. The order may be a little bit different. But those two angles are bubbling up to the top is the key for that particular transition. Now, the one thing that we want to do to follow this up is to construct a coarse representation of the reaction coordinate by taking just the key features, do a free energy profile, and see how well it describes the actual free energy difference. And then we'll add features, bit by bit from this list until the thing converges and see how many we need to actually generate that free energy difference. Okay. Next example is a really interesting problem. This is an example of a small object called a peptoid. All right, the difference between a peptide and a peptoid is that you put the side chain on the avid nitrogen rather than on the alpha carbon. All right, and these things are kind of being considered as very interesting biomimetics. They have features in common with peptides, but they're not actually subject to proteolytic degradation because they're not recognized by proteases. All right, so we do the same thing. We generate experimental committer values, and you get a distribution that looks like this. You run your free energy landscape. We projected it down for you into either phi psi or this omega and psi angle. And what we want to look at is this kind of cis to trans conformational change. All right, so there are 66 dihedral angles on this thing. We're enhancing the sampling of 5 to explore our landscape, so it's a 5-dimensional landscape. And again, we pick out these two interesting conformations. I want to know how I get from one to the other. All right, so we do the same thing. You train your committers, you compare all the different machine learning methods. And once again, the light gradient boosting is doing the best, with the extra trees kind of coming out as the second place one. And that's true for both methods 1 and methods 2.
Mark, all three tetrahedrals flexible here, or is there something like a torsion, like a, what's it called, peptide plane?
Say it again. What?
Is there something?
Oh, you mean like they're all flexible in this case? Yeah, you don't have a nice the omega angle in peptides is pretty rigid, right? That's not the case here. Yeah. Okay. Again, looking at your ability to reproduce the experimental values and light gradient boosting for the committer or the reaction coordinate, you're doing pretty well in both cases. And our SHAP plots, right? What do the SHAP plots show? So the SHAP plots show that the most important angles in this case are the psi and the omega angles. So that's the psi angle, that's the omega. These are just, again, different flavors of them with different indices, but it's basically rotation about the same bond. In order to get to phi, you've got to come down here, all right? So again, we're going to follow this up and try to see, how many features we need to add before our free energy ultimately converges to the free energy difference that we want. Okay, one thing you can actually look at then is the mechanism of the transformation, because you have the actual reaction coordinate. In other words, you can follow from high committer values down to low committer values, basically B to A, or go the other way and go A to B, and looking at the angles of most interest, the psi, the omega, and a little bit this phi angle. And you can see how these things are actually changing as you go from one state or one conformation to the other. In other words, phi and psi apparently are decreasing. Psi is decreasing, whereas the omega angles are increasing. The way it's a little bit intuitive, but that's actually what you find along this reaction path. Okay, and the last thing, just I won't go into this yet because we don't have any results, but we're now going to the next level of complication. So the thing we really want to apply this to ultimately are nucleotides, for example, RNA segments. And these we want to do in full explicit solvent with ions and things like that. In order the complexity of even a dinucleotide is considerably more than a dipeptide or a dipeptoid. And in order to treat the solvent, we're going to have to add some additional descriptors in. So, in addition to some set of dihedral angles, the ones that are the most flexible, we'll need to add in some environmental functions that pick out, the local environment. So for that, we're using these Baylor-Parinello symmetry functions. And so far, we've got about 152 of them to describe all the local environments that we need. So hopefully next time I talk about this, we'll have some results on this. And we might try this recent method for selecting important descriptors, but this is all preliminary work. Okay, so maybe I'll just conclude because I'm probably running out of time. So first of all, I've showed you, the interoperability of our temperature boosting approach and metadynamics and umbrella sampling, which is kind of an ideal thing to combine with machine learning to generate these high-dimensional landscapes, because you get a nice little scattering of points over your landscape, and the features of the free energy surface emerge as you add more and more points. And you can capture those within a machine learning model, just simple regression, all right? Once you have a large set of redundant CVs, you can map out this landscape, find basins of interest that you want to study, between which you want to study transitions. And different ways to do that are based on committer learning. So you either map these CVs directly onto the committer or onto a reaction coordinate. And then all the different machine learning methods that we employed to reproduce these committers. We found this light gradient boosting method performed the best. We'll keep testing these to see if that remains true as we increase the complexity. And finally, we found this SHAP analysis tool to be particularly useful in trying to then reduce the number of features to just a few key ones, out of which you can build your reaction coordinate or your committer and kind of really get it down to just a few essential degrees of freedom that you can use to study these processes. All right, so I think that's my last slide. So thanks, and I'm happy to take any questions.